First, as usual, let me thank the organizers, the two deans of the class of arts and medicine for arranging these two amazing talks. They are really two amazing talks. The first talk is about quantum geometry. Now, what means quantum geometry? It is a geometry of these tiny objects in the quantum world. You know, perhaps following quantum mechanics, we are living in a discrete world. That means there is an absolute tiny length that is the so-called Planck length. And it is assumed in the standard theory of the universe that in the beginning there was a tiny universe, so to say a baby universe in this size, but with unbelievable concentration of energy. And then it is assumed that by expansion of the universe, step by step, the well-known physical forces, which we know, separated step by step by the expansion process and cooling down the expansion. For example, first the gravitation and then the strong forces, which we know from nuclear power, and then the weak force, which we know from the beta decay, and then the electromagnetic forces. And that is not only a nice theory, but to some degree it can be empirical confirmed vice versa in our high energy accelerators. For example, in Geneva, since the 50s and 60s, it is well known that the weak interaction and the electromagnetic interaction can be unified in a very high energy. And then in the next step, we have at least the physics to describe the unification of this electroweak force with the strong force. And then in the end, there is only nowadays mathematics, more or less, to describe this unification of all forces in this tiny baby universe, which I mentioned before. And the candidate, one candidate to describe that mathematically is string theory. The string theory is a little bit strange because in order to unify mathematically these forces, our three familiar dimensions of spatial dimension and time dimension is not sufficient. You need additional dimension. And so in the simplest form of the string theory, you get a 10-dimensional theory. Now, what does that mean? If you have 4 dimension, 3 dimension for space, and 1 dimension for time, then there are 6 dimensions left. So you have 6-dimensional objects. 6-dimensional objects, for mathematics, no problem to describe it exactly. But our intuition and the layman has no chance to imagine this object. But again, mathematics. You can consider so-called pictures, projections of these higher dimensional objects in the 3-dimensional world. And these are the Calabi-Yau manifolds, which will be considered by our first speakers. And you get amazing pictures, 3-dimensional pictures of these geometrical structures. And me personally, it reminds me of Kepler. Kepler in the antique universe consider the geometric building blocks such as crystals and stars, and that was in the tradition of Plato. Plato believed that the universe is constructed from Platonic, that means geometrical bodies. Now I know all that because in my academic youth I wrote a book about mathematical symmetries in physics. Now, anyway, this topic at the first glance seems to have nothing to do with our second talk. Our second talk will consider sounds of cities, metropolis, and for example, the sounds of Kyoto or the sounds of Vladivostok. That means the sounds, I think, of the traffic in the streets, the voices of people. and industry and machines, things like that. And the composer, our second speaker, arranged very impressive performances, and perhaps in the future he will come up with the sound of Salzburg. I think that would be also amazing. Now, anyway, what has that to do with our first talk? You know, as president, I'm always interested in interdisciplinary connection. I think a lot because sounds, that is not only restricted here to the cities, you know, also in the Platonic tradition, in the tradition of Pythagoras, there was the idea that there is a sound of the whole universe. And the early ideas in antiquity was that there are the proportions of the celestial spheres, and they correspond mathematically to proportions of tones. So you get a celestial harmony. And it is amazing that some years ago a Spanish composer came up, his name I think was Hector Palas, he came up with an opera on string theory. And here the fundamental forces which I mentioned and the strings and so on were represented by human voices and the connections. Very amazing idea. So the message of this evening, I think, will again be, we had this message for several times, behind all phenomena which we can experience, there seems to be a kind of mathematics and which can be expressed in music. So we will have again an exciting evening, and I hope very amazing discussions. Thank you for your attention.
Thank you, Klaus. Thank you, Klaus. Wonderful introduction again. Now, Violeta, it's your turn. Thank you.
Thank you. Thank you. I am very, very happy to have the possibility to have here our guest, Andrea Brini. He is a professor of mathematical physics at the University of Sheffield. He did his studies in physics cum laude in Milan and got his PhD in mathematical physics at the International School of Advanced Studies in Trieste. In 2009, he under the supervision of Boris Dubrovin and Alessandro Tanzini. He then spent time as a postdoctoral position funded by the Swiss National Science Foundation at the University of Genova, later at the Imperial College in London. Andrea Brini obtained a research institute in Montpellier, France, permanent research post based at the University of Montpellier, and held visiting research positions again at the Imperial College and Simmons Laufer Mathematical Science Institute in Berkeley, following which he took up an academic post in Birmingham, and he joined the University of Sheffield in 2019 while on leave from the University of Montpellier. I'm very happy to invite you. Have the floor, Andrea.
Thank you very much. I'm just going to pull up my slides. Let's see if you can see them. Are these visible for everyone? Hopefully they are.
Yes, they are.
Okay, well, thank you very much, first of all, for the invitation. I'm obviously humbled by the possibility to give this talk. And I had a fantastic introduction. I wonder whether I should give a talk at all, since the introduction was so good and covered much of what I will talk about. But nonetheless, at the cost of some repetition, let me try and explain what the title of the talk is about. So the talk is, at least in the first approximation, it won't contain, let's see if I can scroll down. Right. So in the first approximation, it's it won't have an artistic dimension, artistic element attached to it. Although I will have some cool pictures, and well, the musical dimension of the talk will be limited to, I guess, my own Italian accent, love it or loathe it. So to a first approximation, it's an intradisciplinary, rather interdisciplinary talk. And it's about a familiar connection about two subjects that have historically been closely aligned, mathematics and physics. What could perhaps be novel about the talk today is that the connection I'm going to talk about has something to do with two subjects that have no a priori connection with each other. So the mathematics will be geometrical across this talk, rather than say analytical. I won't write say partial differential equations in this talk for the most part. And when I say geometrical, I will be mostly concerned by geometry of shapes defined by polynomial equations, so algebraic geometry, and of counting problems therein. And the physical counterpart, this will be quantum mechanical. So it will have to do with our lens on the microscopic world. And more specifically, as was mentioned in the introduction, I will be restricting my attention to a class of systems that are relativistic and that enjoy some special symmetry. It will be supersymmetric. And I guess what's most important in this slide, which is the takeaway message of this talk, is the intersection sign. So the intersection between these two topics is unexpected, no matter how you look at it, even if you look at it as a pure mathematician or, say, as a quantum physicist. So from the physical perspective, the geometry that I'm going to talk about has nothing to do with the geometry of, say, the physical system that you will be looking at. It's not going to be the geometry of space-time. It will be a dynamically emergent notion of geometry that has got to do, for example, with the unification of couplings that was mentioned in the introduction. And the connection is even more surprising from the vantage point of a geometer, of a pure mathematician, in that the physical realization of geometrical problems comes with an array of solutions that will be very difficult to concoct, to come up with in the first place from just a mathematical perspective. So the talk will be in three steps, but really two. First of all, I will try and explain what enumerative problems are in geometry, how they come about, why they're relevant. And the second part of the talk will turn around a citation, so a quote from Eugene Wigner about the unreasonable effectiveness of mathematics in describing quantum physics. I will describe an example where quantum physics is unreasonably effective in solving a mathematical problem without an apparent connection to it in the first place. And if time permits, I will describe a little bit of we'll switch slightly to autobiography, and I'll give a 30 seconds presentation of a recent theorem that I proved at the end of last year, where this is exemplified in a particular case. So without further ado, I'm going to be talking most of the time to the furthest person in the room, in this virtual room from me, so I'm not going to expect that people have a mathematical background. So let me try to introduce the two words in the title, quantum geometry. So what is geometry? Well, geometry can be phrased as the art of understanding space or shape from a mathematical point of view. And so what that means is, well, something that has proved incredibly fruitful in the mathematical description of or understanding of space is the fact that we can attach numbers to describe it. For example, we can, I could describe the geometry of this virtual room by attaching, say, GPS coordinates to each and every one of you present today, telling you your location on the surface of the Earth, imagine as a round sphere. And familiar examples from analytic geometry are, for example, the description of conics, ellipses, hyperbolas, parabolas, as being loci in the plane that are cut by some equation of equal to. So in this picture, there are this setup where I'm considering shapes that are cut by some equation, defined by some equation in some ambient space. Throughout the talk today, I'm going to restrict my attention to simple functions that are just polynomials, possibly many variables. So there won't be, say, exponentials or logarithms across this talk. So the three shapes that you see in this slide are a realization of actually a solution of the Einstein equations in various dimensions. So for the last two, I'm looking at some section of these shapes. So the first is a torus, which in particular conditions can be seen as the solution of a cubic equation in two complex variables. So it would be a complex one-dimensional curve or two-dimensional surface. The picture in the middle is a real section of what's called a K3 surface. So that's the zero locus, the solution of a quartic equation in three complex variables. And I'm looking at the real section of that. And the last picture is of something that that appeared in the presentation. It's a real section of a Calabi-Yau triple. It's the zero locus of so the space of solution of a quintic equation and the polynomial equation of degree 5 in four complex variables. So what does it mean to understand these shapes? Well, there are, broadly speaking, in what is the job description of a geometer? Well, there are two fundamental questions that geometers tackle. What they want to do is to characterize a geometric shape as much as possible and as completely as possible. And then there's a second element, which is kind of sort of botanist element, and it's like sort of linear dimension of the job of a mathematician, which is classification. So can we create, say, a periodic table of shapes with certain properties? So let me break these two questions in accordingly. So the first question we'd be tasked with the problem of characterizing a space completely. And this can be done at two levels. So we can detect properties of space by looking at the small scale. So think of the space around us. So already by just having a look at the universe through the vantage point of our own room, we can see something about, say, its dimension in terms of how many coordinates we need to describe it. And then other properties that we can see already in the small in our room is how, or in relatively small space, or relatively small scales, is how the space bends. So properties like curvature, and whether this curvature explodes to give singularities, so some kind of spikes in the geometry. So these are properties of space that emerge from a local analysis. And then there are properties that are only seen from afar, kind of subspecie eternitatis, kind of view from eternity on a shape. So there are large-scale properties. For example, answering the question, is a space bounded and how is it bounded? Or what kind of symmetries does it have globally? Or does it have any holes, and do they affect the kind of structures that the space can sustain? So one is, this is the sort of main question, and the sub-question, which is sort of weaker, is if you're given two mathematical shapes, x and y, are they the same? And when I say are they the same, I'm asking, are they intrinsically the same, or is the difference between them just in the eye of the beholder? So suppose they're defined by two different equations. Is there a way to, say, morph space y into space x by a change of perspective, which would be a change of coordinates? And of course, underlying this question is what kind of freedom I have to morph one shape into another. So if I have, say, two ellipses, if I'm only allowing myself to rotate rigidly the plane where they're in, then I might fail to morph one into the other because the eccentricities wouldn't match. But if I'm allowing linear changes of coordinates where I can squeeze them, I can always match one to the other. But on the other hand, I won't be able to match ever an ellipsis with a hyperbola. So there could be obstructions in how you match two spaces, whether you say that they are the same or not. So this is the job description. How do we carry out this job? In principle, the question is simple, and it's a hard one. So simple doesn't mean easy. One could say, well, we have this presentations as spaces being cut by some equation, say the equation of a circle, x squared plus y squared minus 1 equals 0. And then we need to see whether we can reduce two things to the same one, the same equation. And the difficulty with that is these changes of coordinates are difficult to guess. So it's not just a matter of guesswork, is borderline impossible. But also these presentations are preciously rare. So usually we don't have these global descriptions of geometric spaces. We need to patch them up from some local description in a complicated way. So it's very indirect how a geometric space is described. So how do we overcome this? And so a key idea from the 19th century is to attach invariants to geometry. So we can construct some algebraic or numerical quantities attached to a space that are insensitive to the eye of the beholder. They don't vary when we morph one shape into another. So if we're able to measure a discrepancy between the invariance of x and the invariance of y, then we would be able to tell that they're not the same shape. So the sort of next level question is, since these are important tools, how can we construct them? So how can we construct all invariants of a geometric space? And there's plenty of ways. And I'm going to consider just one example. I want to probe the geometry of a space mathematically by looking at what kind of objects I can fit into it. So this is you can see a plastic depiction of what academic life looks like, especially in our early years. We're moving from one place to another. In my case, it's been, I guess, a different house every 18 months for 10 years. And we have our stuff that we carry with us. And when you are in that position, in the UK, we have these big storages at the outskirts of the cities, like ugly yellow buildings that have rooms where you can put your stuff. And if you want to save money, you can actually get the cheaper room by taking something that, for example, has a beam through it, or it has an irregular shape. Now, not only would you save money by picking that room, but there's an interesting mathematical problem. There is non-trivial geometry at play. For example, that space can be multiply connected because you have a column in the middle that you want to avoid in order to put your stuff in it. So perhaps less informally, you would be asking yourself, well, how can I understand some class of objects, subspaces, in a given space, and how would that help me in understanding the parent space? Well, per se, this is just complicating your life. You're just replicating the original question that you had for your space X about every subset of X, including X itself. So if the problem was hard, now it's exponentially hard. However, you can simplify the problem by making some choices. You're not looking at just any type of objects, any type of subspace in a given space. You can look at spaces that satisfy a simple property. For example, you're looking at subspaces that have a given dimension. For example, you just look at curves that live in this space or surfaces. And then regarding this set of sub-objects of X, you can ask some questions. Something that you can do, for example, in homology theory is realizing things up to some suitable equivalence relation. And this is how the invariants of algebraic topology arise. And the angle that I want to take in my talk today is I actually want to touch numbers that arise from a crude enumeration. So the question that I want to ask about these boxes or whatever objects that I'm going to look at in this ambient space is the crudest of all questions. The question is how many? So if I have, for example, some continuous space parameterizing these objects, I would be interested in some volume with some canonical volume form. If it's a discrete finite set, I'm interested in the cardinality of that set. And what's the use of this? Well, I can look at different objects with different properties. And I have a lot of choices in terms of the properties that I specify. And since I have an infinite set of choices for these properties, that gives me a sort of infinite infinitely large data set of invariants of my geometry. So again, I can use this number as some sort of biometric passport of my space. And if I solve this counting, these enumerative problems for two different spaces, I can use them to distinguish and classify them. So let me start with one example. Well, what time did I start? Did I start at 10 past? Just so I know how I'm doing with time. I wouldn't want to eat in the time of the next speaker. I guess so. Yeah, interrupt me if I overrun. So in this case, let's take as a space the screen that you're looking at. So as an example of a plane. And for my purposes, I would like to think of this plane as a complex plane, and I would like to think it as some sort of compact bounded object. So we'll take the complex projective plane, CP2, but that probably doesn't matter. That doesn't matter for the questions that I'm going to ask. And the enumerative problem that I want to ask is, well, the property is to be a curve in this space of a certain degree. Let's start from the simplest case, which is curves of degree 1. That's a line. And the property is how many pass through a suitable number of points in order to get a suitable finite count. So how many lines pass through 2 points in the plane? And assuming that these 2 points are not coincident, oops, this was very bad. We know the answer. Since Euclid, this is only 1. And so let's turn the temperature up by 1 notch, and let's look at curves of degree 2 in the plane that pass through, again, the suitable number of points to single out a finite number of them. And this will be 5 points in the plane. So what's the answer to that? I guess we can get our fingers out. Conic is defined by a degree 2 equation. That's 6 parameters. That's x squared, xy, y squared, xy, and the degree 0 term. An equation is defined by taking these parameters up to scaling. So I have 5 free parameters. So specifying a point is a linear condition on these parameters. If I specify 5 points, I have a linear system of 5 equations in 5 variables. And if the points are generic, the system is generic. So this will allow a single solution, which was found, I guess, a couple of Ptolemaic kings after Euclid by Apollonius of Perga originally. Again, let's turn the temperature up 1 notch, and we'll look at rational curves of degree 1, degree 2. Let's look at degree 3, rational cubics. And then let's look at them through the suitable number of points, which is 8. And in this case, you would think that every point specifies a linear condition on the parameters defining this cubic polynomial. And that the answer would be 1 again. And the answer turns out to be 12 instead. And the reason why the answer is not 1 is because of this word rational that I've added. So all lines and conics are plane lines and conics are genus 0 curves, but a cubic is generically an elliptic curve. And so if I specify that my cubic is rational, that's a nonlinear condition on the parameters of the equation that specify it. And this will give me some polynomial constraint. In particular, if I specify 8 points, that will specify a pencil of cubics. And the count of rational cubics will be the count of singular fibers, which I have Euler characteristic 1. So if I want to compute this number n3, I need to take the Euler characteristic of the total space, which turns out to be the plane blown up at 9 points. So 3 plus 9 is 12. If you follow the argument, that's great. If you didn't follow the argument, the message is this is no longer high school mathematics. It gets really, really hard when you raise the degree. So understandably, it gets even harder when you look at degree 4 equations through 11 points. The answer is 620. And it gets even harder, and it gets to, the answer was found in the 80s, I believe, 80s and then late 90s in a succession of 2 papers when you look at degree 5 equations through 14 points. With the expectation that there would be no answer to the case of a general count of rational degree D curves through 3D minus 1 points in the plane. So this was something for the 22nd century or something. Turns out the answer appeared the next year, and it's a full recursion for all degrees in one go, just from knowing the answer for degree 1, the one for lines. this was like godsend. It came from magic. The magic has a name, is quantum mechanics. So it turns out that this same problem, this enumeration of objects, can be seen as arising, the space of objects can be realized as the set of classical trajectories for a quantum mechanical system, which in this case is something that is called a topological sigma model, something that describes the propagation of strings at the classical level with target the plane CP2. So there's a particularly so-called supersymmetric theory, which allows something called a topological twist. And in quantum mechanics, you would be ordered to, if you wanted to compute observable in quantum mechanics, you would need to perform some sum over histories. This is something that came out of Richard Feynman's PhD thesis, with the classical trajectory kind of maximizing or extremizing the action of the system. And the magic of supersymmetry is that all the quantum trajectories, the virtual ones, are suppressed in this topological setting, and only the classical ones, the ones that actually represent our actual count, contribute to the sum. So our original number comes out as some quantum mechanical observable, and physics tells us how to compute these quantum mechanical observables. There is some crossing symmetry for a 4-point function in the plane, in a certain chiral operator for this topological sigma model. And you can write a differential equation that governs this symmetry. It's some bilinear equation in the triple derivatives of this partition function. And if you just look at what this is at the level of the coefficients, it gives you some bilinear, some nonlinear recursion at the level of this coefficients n, which is exactly this concierge recursion that solved our problems to all degrees. So somehow physics holds the key to an answer to the answer of problems that will be extremely difficult to address using purely geometrical terms. You have to think like a physicist if you want to find the answer. And there's an impressive list of shortcuts that physics gives through the notion of duality. Sometimes different physical systems, well, the same physical systems allows for two different descriptions that are even more different when you look at them in terms of their rigorous mathematical realization. So for example, if you wanted to consider invariance of knots in our three-dimensional Euclidean space, this can be realized by some so-called quantum gauge theory. And there's a relation between gauge theory and string theory that relates this topological invariance of knots to invariance of curves in a given Calabi-Yau manifold, some completely algebra geometric object that has no relation whatsoever with the real geometry of knots in free space. And then string theory dualities would relate that to problems in singularity theory, which are in turn covered by some number theoretic objects like modular forms. This would be impossible to guess from the mathematics alone, and somehow the heuristics of the physics is what guides us with the drawback that as a physicist you have some poetic licenses. You can do away with rigor, at least for a while. But you do want that rigor back, and recent developments have seen mathematicians kind of catching up and rigorizing all these connections between different theories of invariance in geometry as related through some physics motivated duality. And I'm just going to mention the latest development as far as I'm concerned, which is something to do again with a complex projective plane, but it's not a plane itself. It's a plane sitting in this famous Calabi-Yau manifolds. So if you just look at the geometry close by a projective plane, a neighborhood of CP2 in a Calabi-Yau 3 is a total space of some line bundle O minus 3P2. And one can compute all the invariants of this geometry, provided that a certain universality property is proved for the behavior of these generating functions. And it is something that was proved last September by realizing some physical expectation about a relation with a certain statistical mechanical system of repulsive particles on the positive half line. So this is when I was talking about the biometric passport of a shape. This is the kind of, maybe I can zoom. These are the kind of is a kind of data that you're able to extract, and they are unique to this geometry. And with that said, I believe I'm out of time. So thank you very much for your attention.
Incredible. I was feeling accelerando, crescendo until an incredible climax. I didn't understand, but I am so fascinated. But we have here personalities who understand a lot. But it's really wonderful. Andrea, thank you so much. Thank you very much. Now, I have the pleasure to invite Joannou Elia. He's a composer, academician, cultural leader whose works merges music, space, technology, collective memory. Describe the American multinational news media. It describes him the child prodigy of contemporary music and the man for monumental events. He is internationally known for large-scale polymedial creations, gained global recognition with Auto Symphonic in Mannheim in 2011, and he held the work of the century. His ongoing sound of series reimagines cities through sound and audiovisual architecture worldwide. Klaus Mainzer told us about. Elia's recent works include Liberty, Gaia, The Earth's Song, Philia, Ode to Friendship, and Aima, Blood. His music has been performed by leading orchestras internationally, and he has received over 50 international awards. Elia is also a member of EASA. Please, Marios. You have to unmute you. Unmute, Marios. Try again. Otherwise, we begin to sing for you. We shall have a cosmical sound coming from all over the world. Andrea, I'm so happy you were with us. I must tell you that Andrea began in his life to learn Greek and Latin and studied philosophy in a very deep way until he would try to find answers deeper than only thoughts of the philosophy. For me, it's like an incredible phenomenon. I'm very happy I had the possibility because Andrea is so occupied and he has so much to do and to think.
No, is it true? Is it true? Let me ask. Is it true Andrea was born in 1954?
That's an interesting one. So there are two Andrea Brinis. There are mathematicians, and that is okay.
Yeah.
Maybe I should.
He's younger.
This is getting to YouTube, right? I have some hilarious stories to tell, but I won't be able to tell them on record.
Because you look so young. I mean,
yeah. I mean, I've been mistaken for the other, and I don't know if that the converse also happened in a number of hilarious exchanges.
But your university is?
So I have a dual position. I'm a professor in the University of Sheffield, and I have a position at CNRS in France. And there's an algebraist. I think he's just recently retired at the University of Bologna.
Yes.
Incredible. I discovered also when I discovered his biography, he's on leave from the University of Montpellier. Great.
I am back.
Unique.
Like Schwarzenegger.
Okay, good. Hello, Marios. Thank you for coming.
So I'm trying to connect. So I hope it's visible. So am I able to be heard? Yes? Okay. So first of all, thank you for the lovely introduction to you, dear Violeta, also to you, dear President Mainzer. I am thinking of making a very short introduction, so maybe some members of the Academy or guests might not be able to have seen the presentation we had some years ago within this colloquium. So in order to be able to understand the concept behind this musicalization of geographical sites. So And today I would like to focus on the project Sound of Shanghai. This is the third part of the trilogy that started in Vladivostok, continued in Kyoto, and then in Shanghai. But before going there, I would like to shortly introduce the concept behind this approach. This is the so-called concept of polymediality. As you might recognize, there is a paradigm shift. We are not speaking about multimediality, but the multi-prefix has been replaced by poly. This might remind you of polyphony, polyrhythm, or polytonality. And this goes back to the Aristotelian conception of the sense-establishing ratio between the parts that constitute a whole. And this concept has two dimensions. The one is the word immanent compositional dimension, and the second one is polymediality in the process of staging. It has been said before, the project or the open-air multimedia symphony, auto-symphonic. I would very like to introduce this to you, because this is a very good example how it also led the way to the sound of cycle. So this is the central square of Mannheim, Friedrichsplatz. Maybe some of you might know. So this is before the preparations for the concert, and this is the concert and the whole staging concept, which includes both dimensions of polymediality. So, and what is special in the instrumentarium, which is the works immanent polymediality, this is an orchestra consisting of 80 mobiles, which you can see a part of it here. So, and in order to build the orchestra, there have been castings, and the individual sounds of the cars, in this case, a Ferrari, have been recorded, and then they have been listed. So in the case, these are the various instruments on the left side. So you can see Rolls-Royce, some executive cars by BMW, and so on. And all the way through the different techniques and how they can be performed, what sounds and frequencies they correspond to, that is the pitch, and how they are practically or not, so that we can consider on the notation their performative qualities. And this is how a car is being performed. So these are the various stages, how it all started from the casting all the way through how it goes on stage. And what about the orchestra and choir? Because there is a main turning point here. Our President Mainzer spoke about sounds of the cities and so on. It's not just this. This is the source. This is the material. And it gets to a different reproduction perception. I would call it through the compositional process, and I will explain what this means. And in this case, cars, they don't stand alone in the performative field, but they stand on the opposite side of an orchestra and a choir. And here you see a notation how, in a way, daily life, in this case, this traffic directive sign becomes music for 32 voices. There are cars and so on. So the polymediality in the process of staging concerns all these extra musical elements that have been applied and synchronized to the music. And in this case of this project, this is an immense volume of technical stuff, like 296 loudspeakers. And this is the square, how we have seen in the beginning of the presentation. It's in a 360 degrees, and it is a kind of negative amphitheater. It's not the events that are in the center, but in the center is the audience, and all around in 360 degrees are the events happening. And in this case, this is the stage, the main floor for the orchestra, surrounded by LEDs and elsewhere. And on the other side, what you see all around, it's the car orchestra and 120 musicians. And the audience and the audiovisual actions are all around this place. So I have a part, maybe I play a little bit so to make a little musical break and we continue.
This is no sound. Everybody reacted. Marios, please, do you have the possibility that we can listen also something? No sound.
Oh,
Can you put it again, please? I didn't dare to stop, but there are others also.
Oh, I thought.
Can you try again?
Because I was hearing it, I thought, it sounds okay here. Now, can you hear something?
You can actually reshare the slides and then you can click something, you know. You can reshare the slide, stop sharing,
Yes.
and then you see there are different options. There were one to when you share the slides, they have an option to share the sound from the slides. You have to click that one.
Where is this one? Do you know?
When you plan to share the slides from the Zoom, you click the share. There are the buttons maybe on the button or on the right side. You can see it. There was a small button to click it. Then the sound will be shown.
Maybe I stop share. Okay. Now, where shall I go? Now I am in Zoom, yes?
Yeah, you are in the Zoom and you can really, you plan to share the screen?
Yes.
Yeah, when you see this, when you plan to share, there are some notes. There are different options.
Okay.
Yeah,
Now
you
I
have to
think
click that one. So click this down.
it's
Yeah. Yeah, now it's worked. Yeah. Now it's working. Yeah, great.
something happened.
But
Someone else is sharing. I read here.
It's interesting. We have to see it. Can you try again?
No, there is a
To see and
notification
listen.
that someone else is sharing. I don't know what it means. So. I don't know why, but the flow was interrupted. Now?
Yeah, it's possible to listen.
Okay.
Yeah, we listen, but we do not see anything.
No?
No, but doesn't matter. So at least we can listen to something.
Professor, maybe you can reshare your slides again.
I got a notification, but someone tried to share his screen. Let's see.
So maybe we just listen for 1 minute at least.
Yes, but
and then you
somehow
continue.
I think the sharing of the
Because we saw
screen,
something. Yeah.
the share of the screen has been interrupted for a reason, and I don't know why. Barry, do you know what can I do here now?
Professor, I think you can just try to reshare your slides and remember to click that button. Because now no one is sharing now, so you can just reshare your slides.
Somehow I don't see our chat anymore.
Violeta, you are not sharing anything, right? This is from someone else's screen, so you are muted. Violeta, you are muted.
Yeah, I have here, I can stop share, but I don't.
Yeah,
do I have to stop share?
Yes, you have to stop share.
I stopped share before.
Yeah, now Mario, you can try again. So sorry.
No. Somehow now I don't see my screen. Maybe I rejoin the Zoom. Okay. Now it's visible, hopefully.
Yeah, it's possible. We see, but we don't listen, hear anything.
Now?
Yeah, now it's worked.
Wonderful. Yeah.
So I think I will continue because time is running up. Can you hear me now?
Yes.
Yes? Okay. So the previous project was created for celebrating the automobile, which was invented in the city where the concert took place. And the festive reason became the subject for the music. And for this, the whole city was activated to perform this piece. And this idea leads to the concept whether, or to the question whether each city has its own sound. And in 2017, the first part of, for the moment, tricycle took place in Vladivostok, and then in Kyoto, and currently in Shanghai. And then in order to answer this question, there is a very simple equation idea, which is the musicalization of a topos, a place, plus the implementation, which constitutes music composition and field recording, results to a film concept with which all these topos, the entire polytope, is being put together, accompanied with image. And the result is a cinematic film concept in the spatial sound surround system. So, as we said before, 3 cities, each one is selected on purpose because it has something very specific. Vladivostok, it's the end of the world or the beginning of the new world. Then Kyoto was the imperial capital of Japan. And currently Shanghai, China's gateway to modernity. And very shortly here, this is from Vladivostok. It shows the different spots where actions, either recording or music performances took place. And then the presentation is either in the form of a concert, like here in the Philharmonic with the symphony and the choir on stage, or in a cinema with this sound surround format. Moving to Kyoto, I don't know how much time we have. I will go through this film. And here, a short explanation what concert soundscapes and field recordings and sounds that are taken from the city or from different aspects that are within this geographical scope. Here, the turning point is not a reproduction in the project of a sound that is being recorded, but it has been also a compositional approach to soundscapes. And a very simple example to explain it is that one sound is not being recorded at one moment or at one position. Several microphones at different time of a day are being recorded, and all these different recordings, they are being put together like a chord. So, and the result is a kind of polyphony, which is actually an artificial result of reality. And when it's being mixed, and here it's the sound of the bamboo forest Sagano. This is one of the 100 preserved soundscapes listed by the environmental ministry of Japan. And this sound that you will hear also now is now part of a book that is going to come out soon about the forest of the world. And this polyphonic field recording sounds like this. So what you see here is not the result. This is just the part of the process. And before I go to Shanghai, I would like to shortly play the trailer of Sound of Kyoto. and now to the current part of this cycle, Sound of Shanghai. It's going to be premiered coming June in Shanghai. Therefore, I will be able to show some behind the scenes, in a way, parts of this project. So the idea behind it, and as the subtitle says, opera in a cosmopolis, it draws back to the idea that the so-called Kuhn opera, which is a very specific aesthetical operatic genre, was born in the outskirts of Shanghai, and the city is being staged, as you have seen, for example, now in Kyoto. So therefore, the stage for this operatic approach is the metropolis or cosmopolis of Shanghai. And there is a list here over 250 musicians, 6,500, actually almost 7,000 audio and video clips, 90 locations have been used as performative stages, and over 30 institutions have been involved. And the pillars of the project, and this is, I think, an overview of everything that we have seen before. There is music, there are certain groups for which I compose specifically music and they perform it. Then there are the sounds that reflect the identity or the cultural background of the city, like goom embroidery or teapot rhythms. We'll see a short example later. And then the different performance spaces, they can be indoor or outdoor. In Shanghai, I used also the top of a skyscraper. And then the last element, as you have seen before, it's the cinematography. This is the film. This is not something that comes afterwards, but this is a part of the concept of polymediality. The music and the image, in a way, are being composed parallel and set by the composer in its music score. And in this case of Shanghai, they have been set different drones and other techniques that are related to the image. Hawaiian opera, we have explained it before. Here shortly the main orchestra. So what I used very strongly in this project, there are the traditional or the folklore instruments of China, and in first place the National Chinese Orchestra, in second place the Guzheng Orchestra and the Ruan Orchestra. This was the main corpus of the National Chinese Orchestra, and as you might see in the center, there are some Western European instruments like cello and contrabasses in the back, or a harp, and this goes back to the reason that Shanghai has a very strong influence with Western civilization. Shortly, for our music friends, these are the main instrumentarium and the instruments that consist the Chinese orchestra, 95 musicians, and this is the second group. This is a Guzheng orchestra, very high talented musicians, and here I can play a little bit, so how it sounds. And then how it sounds better. And to this same group, I have added a choir. So the performance sync. This is the second group. This is set on the top of a skyscraper in front of the band. I'm sure some of you have visited Shanghai. So, and the performance is being filmed here. Then another group is a kindergarten choir, and this reflects the different generations that are important in every part of these projects. And here is the jazz club, which is in a way the more contemporary sound in the project. And this is associated with the fact that in the 1920s, Shanghai was the center of the jazz world in Asia. And what you see here on the right, these are the so-called Qipao. This is, let's say, the evolution of the Chinese culture in the beginning of the 20th century, with this close in the same period where the jazz has been evolved. And as we all know, China is a populated city, so footsteps are a very typical element. And in this case, we have been recording here. As you hear, they have been recorded rhythmically because then they play a rhythmical element within the music. So, and then on the contrary, this is the crowd's different footsteps that have been recorded here. Regarding the different sound elements that reflect the cultural heritage of Shanghai, here is a part of a gastronomic session, I will call it. This is a Michelin star that all consists of dishes that are being made with the ingredient of tea, among others. And here is another rhythmical element that is being taken from this framework, and it sounds like this. So, and this woman, she's the main actor, the protagonist in the opera of Cosmopolis. And she's being placed among others in the boat, which is a nearby city, which is called the Venice of Shanghai. And here it is evident how the cinematography comes in play behind the scenes. So how the film is being made. And finally, I would like to show a more modernistic element of the project. What you see here, it's a band around the head. This is a band that records my brain waves, and the brain waves are being sent on this algorithm, which are being created especially to translate brain waves into sounds. And this algorithm has different parameters with which I can, in a way, transfer and manipulate my brain waves, and as a result, gain different sounds. So the same has been put in image. What I didn't mention before was that there is a source that has been used as inspiration and as a code, I would say, for this opera. And this is a very well-known play in Chinese culture, the peony pavilion. Peony is a kind of flower. And I use a very short melody it's not so much recognized in the instrumental part, but there is a moment where the original character appears. And here we transfer the peony image into this more, I would say, well, modern age peony. So the music was from the Chinese orchestra. And behind the recording, there has been a very demanding concept and how it has been realized, but I will not go here in depth. And the result is going to be in this so-called spatial surround system based on the wave field synthesis. And this is what you see here in the studio. All around, there are these black boxes. These are speakers, and this the sound moves from the one speaker to the next, and that's why we say the sound moves with its corpus. It's not virtually as we usually hear in a stereo format. So, and here, as we started, what we see here, it's a performance. And you see on my head, I carry this mechanism which records my brain. And in this performance here, there is a camera underneath me, and it controls or it records the moving of my hand. And the movement of my hand controls the lights around me. At the same time, there are the lights in the skyscrapers, as you might remember at the beginning. So there is interaction from the body to sound and image, and the whole space is being integrated. So I think I have come on time to an end. Thank you very much for your attention.
Thank you very much, Marios, also. And I would like to invite you for the discussion. Please help me if I do not discover who is going to say something, because I can't see very well who is going to. Who may I invite to tell something, please? Tassos, you began to ask something, Andrea. May I ask you again? Where are you? Tassos, I don't see him. So, anyway, I would like to ask you, Marios, how long is such a piece? It's
you mean the duration or the production?
No, duration.
Duration is 23.5 minutes.
Okay.
The duration of the film. So the music is around 40 minutes, but in the film we just take, let's say, a duration that is very practical to be screened in various occasions. So there is an average of 25 minutes. So we decided to have 20.
Thank you. Excuse me. I don't know who was first, Livia or Klaus. May I invite Livia? Ladies first. Livia, please.
Hello, everybody. Hello, Marios. I'm fascinated. I knew about your works, but the real presentation was fantastic and overwhelming. I mean, I think nothing was left behind. So my question is, what do you think? What is the ratio between cultural heritage, so identical cultural identity of each city or space, and your enhancement of it with several sources, like the woods sounds, like your own brain Yes, why not, you know, the sound of the sun? You can find it on the on NASA.
If there is sound in the sun and not just we burn ourselves, only the sound of burning.
Only the
Well,
sound. Yes. So you understood my question. So
yeah,
anyway.
I will try to answer. If I didn't understand very well, please hands up.
Yes.
So if I understood well, you mean what's the percentage of the cultural heritage and the percentage of original creation?
and original not original conception, because you enhanced the identity of each
Yes.
you enhanced with geographical sounds, with not only with the melody and specificity of the melody, or you understand. So you enhanced, you made a hyper sound of cultural identity, something like this. It's fantastic. Yeah, blowing
very-
my mind.
The complication in this approach is to make this sense establishing ratio. So that's why my aim is not just to make a collection of sounds or to create a kind of sound library, or just to incorporate whatever is being heard and is being recorded. That's why many elements stay outside the final result, because what's important is to make a kind of contextualization between the elements. And maybe a small example to make this more specific. At the beginning of the Sound of Kyoto trailer, you saw a shakuhachi flute. So this shakuhachi flute is made of bamboo. The place where the shakuhachi flute has been performed, it's within a bamboo forest.
Yeah.
The melody has nothing to do with any original Japanese melody. It's a melody that in a way I conceived having this experience in Kyoto. So, and within this context, we try to create a so-called third space. I think there is, I don't know if he's alive, Klapka is he was teaching in Harvard. I don't know if someone knows him. He was specified in this cultural context when places have been colonized. For example, when there is a place, and in case of Shanghai, France comes in, or the French culture, and then there is this hybrid intertextualization between the different cultures. In this case, or in my case, maybe this can be understood with the idea of the peony flower. So we know that in the cultural heritage of China, this Chinese opera, it's something very prominent, but you will never see this artificial, in a way, peony, as it appears in our case. At the same time, I use electronic sounds taken from my brain in this case, and then mixed with the melody of the original that is being taken from the section from this peony pavilion, and then put in a new context with different instruments. And the overall result, it's this third space. So, and it wouldn't be there without what consisted, but it has, in a way, it's being freed from its past. So this is how I understand the approach.
Thank you very much. And now Klaus, my turn.
Yeah, thank you. I have a question to both speakers, but let me start with the last talk. Also for me, absolute fascinating. And I'm looking on your project on the sound profile of the cities from the perspective of the European Academy, because one of our main goal is better understanding the mentality in the different cultures. And I think that is a nice project to visualize and to make it with sounds understandable. What is the difference and what are the similarities? So my idea is, and I mentioned, that's a speculation, I must say. I mentioned Salzburg, And when I hear the different profiles, your profiles on Vladivostok and Shanghai and Kyoto, my first impression, I know Kyoto also very well, my first impression was maybe that the profile of Kyoto, for example, has a lot of in common with Salzburg, because it is the sound of harmony here in the background, the Mozart tradition, and everywhere is Mozart in this small but absolutely fascinating city. And but there are, of course, differences, the Asian tradition and the old European tradition, things like that. So my idea is to connect it with this vision of the European Academy. It's a very nice project. And if you come up with a profile of Salzburg, then we will invite you to the next festive assembly to to give us an impression for that. That's my question to the first to you, Marius, and now to Andrea. Yes, it is well known that nowadays there is a close connection between so-called pure mathematics, like geometry, and at least theoretical physics. And there are influences vice versa, and inspirations. I mentioned, for example, the string theory, the theoretical physics with the Calabi-Yau geometry on the mathematical side. Now, my question is, what is your impression concerning the empirical application? Is there not only an influence between theoretical physics and theoretical mathematics, but is there also input for the empirical research in physics? Thank you.
Who goes first?
Andrea, I think maybe you go first because I spoke before.
Okay. Yeah, thanks a lot for the question. Maybe if I can stick with the relation between theoretical physics for a second, I'm going to move to the experimental bit later. It's perhaps something that was kind of behind the scenes in my talk was how difficult the relationship is. It's actually close to some sort of dysfunctional marriage at times, because pure mathematicians and theoretical physicists don't actually speak the same language. So most of the fascination and the surprise in these connections is the fact that geometers have absolutely no clue what the physicists are saying. It's not like there's a continuous translation between the two. So even the step that would have seemed immediate is actually quite a bit of a, so in physical parlance, first order phase transition. There's a bit of a singularity in how the theoretical mathematicians and theoretical physicists speak. When you move to the empirical realm, the disconnect would be bound to happen. However, and this is not something that I do particularly as part of what I do in my research day-to-day work. There are methods from geometry and topology that recently have stepped into the realm of data analysis, for example. And there are powerful methods. I mentioned, for example, the invariance that can be computed from homological algebra. And these are playing a role when, for example, you have to, I kind of misuse the word data set somehow in my talk, but when you're actually looking at actual experimental data sets, geometric and topological methods are becoming increasingly important, and also algebraic methods in statistical analysis itself. So there is a continuum, of course, and this continuum has some sort of hiccups when it comes to human communication. But that's the fun of the job, I would say.
Marius now.
So, dear Professor Weinzer, thank you very much for this very attractive idea. I must admit that I was looking forward which city could be the first in this series of the sound of concept. And since now the Asian geographical area has been taken in focus, I think Salzburg should be an ideal starting point in Europe, and not least because it's also the seat of our academy. I have lived in Salzburg for 15 years, but I left in 2010, so I have a small gap about the evolvement of the city the last already 15 years. So I think it's a very interesting approach to, in a way, put opposite Kyoto and Salzburg and try to find what is in between. And whether these parallel lines, maybe they well intervene in the way or another. So I think it's something to take into serious consideration. And I thank you very much for this idea. I will go through it. Yes.
So the next world premiere will be in Salzburg. Thank you very much. And may I invite you now, Peter Hermann. Peter? Yeah.
Yeah, should work now. The sound of a city, I'm wondering, well, there are two questions, two dimensions. The one is the sound of a city. The city, isn't it, especially looking at those, Shanghai and others, isn't a city too large as a unit to reflect upon in terms of the city? And another dimension of size is actually there is a sound of a city, there's a sound of its traffic, there's a sound of people. How far would you reflect this explicitly as different points of reference? So yeah. There is a sound of a city as such, but then there are the different subdimensions. Would be interesting for me at least to learn how or in which way should they be made explicit.
Well, the size, of course, comparing Vladivostok over Kyoto and then in Shanghai, 30 million inhabitants, and the whole, I consider also the metropolitan region and the outskirts of a city as well. So practically, it's impossible to focus in every aspect. So what I do usually the first 3 months in such a project is to make a research of what can be of interest and also to focus in one subject. For example, in this case, this operatic idea of and staging in the city of Shanghai, but trying to find a connection between sounds, images, and the music that is going to be composed. So in the end, I make a selection of what I believe it's of interest at that point that I have made this research. So it's impossible to take everything in focus. So the result is actually a selection of what has been practically manageable within the 3 or 6 months that I am able to live in these cities. In Kyoto, for example, I lived 6 months for this project there. The amount of data is big, and the problem is bigger because, as I explained before, my idea is not to make a sound library and present a list of all the possible sounds or images that you have been able to capture, although this is not everything that is present or hearable in the city, but to find such elements so that to make the idea with its holistic approach in order to have an end, a beginning, and an end. So, and for example, in Shanghai, we try to focus in different elements. For example, gastronomy, I was not focused in Kyoto so much or in Vladivostok. So every time I try to find different elements that differ from the projects that have been taken before, and to put them also in a new context. For example, Peony Pavilion, there is the main singer who has this Kun operatic flair, in her voice, and instead of using an orchestra, I use different gastronomic sounds. So she sings in the background of gastronomic sounds. So every time I come also to new ideas, and for me it's also important not to show what is so easily obvious. So people working, it's obvious. Hearing something in the city that everybody hears is obvious, and everybody can record it. My aim is also to find hidden gems, I would say, or elements that are not easy visible, at least to a tourist.
Thank you very much. It is a very strange for me correspondence with the image Andrea showed us. So many things. So you had to decide for so many sources to do something. In fact, This is a definition of composition. Composition componere. That means you have elements and then you have to decide what to do with the elements. It's incredible. May I invite now Robert Mimra?
Hello, everybody. I have a question for Andrea. As a musician with only a basic background in mathematics, I may be misreading this, but I was struck by how strongly quantum geometry seems to rely on global structures, spaces of possibilities, and the summation over many configurations. Rather than on a focus on a single object. And in music, we often work in a similar way, maybe using systems or forms that generate many realizations rather than a single fixed outcome. Do you think that the way quantum geometry replaced individual geometric objects with entire spaces of possibilities could offer a meaningful conceptual model for musical form or composition, even if only metaphorically, I guess?
I'm not confident to address the question at the technical level. At the suggestive level, when I refer to the summation over infinite possibilities, this is something that has a grounding in general in quantum mechanics, even for observable systems. So the kind of systems that I was talking about, they're idealized, they're not realizable as much in a lab, but they have an interesting mathematical component which solves a pure mathematical problem. If you want, it's applied physics to pure mathematics. But when you look at quantum mechanics, even for observable systems, you find something that are called like interference patterns. You know, there's quantum mechanics has at its root some dual nature of reality, where at a microscopic level, particles have a wave nature. And the evolution of quantum mechanical systems, when they have when they have a space dimension, they're not just, for example, spin systems, is something that that has some wave dynamics. And indeed, the role of quantum effects is some sort of superposition of these different solutions, which also includes some non-physical solutions. In the case of the calculation of global geometric invariance that I mentioned before, there's some sort of miracle which kind of suppresses the quantum nature and leaves only a finite dimensional, so a finite number of parameters in the description of the problem, which is what returns the purely geometrical answer. But indeed, I mean, all the keywords are there. Stringing them together, I guess that could be at least an abstract possibility in order to get something meaningful.
Thank you.
So inspiring to discover such new dimensions of our life and of our knowledges. But I tell you, I saw the correspondence between these incredible things. Barry, please.
Yeah, I have the question to Professor Marius because I think it's so fancy, you know, for you to show this how you produce, right, and create the sound of the city. I want to ask, so because now we know how you produce it, how you collect not only the sound, the music, but also the vision, right, the images from the people. And I'm curiously to know, for example, when you show this three different sound of the cities, so what kind of different emotions, right, might be bring to the people? Because I can imagine one for the in Japan, you want to show the history, and in Shanghai, you show the modernism. They have different topics, but I'm also thinking about the people who listen to it or watch it. So, what kind of different emotions, right, can be bring to?
I was very surprised by the emotions of the Russian people. And there is a video where they, in a way, after the first premiere, people speak about their experiences, and there were people from different backgrounds. So, for example, workers and people from the universities and artists and the owner of Beluga Group. So maybe you know Beluga, this big company. So, and in general, and also what is also shown on this video, people even cry. And I was very shocked by this because there are many sub-stories that they can explain the experiences that they had in all these occasions, arrested by the police in Vladivostok when I first came. There was even an article that someone was warning about a spy that is going around and something he's doing with some very weird equipment. And as you know, Vladivostok has been established in order to safeguard the Russian ground to the Pacific region. So they are very patriotic, and I just didn't want to show this military feeling, because at least there is one person in every family that has a connection, if not to the Navy, to the this military culture there. And seeing the sounds of their city and coming out crying, for me, it was like, I was never expecting this. In Kyoto, it's a different culture. They are more.
What happened?
The connections was not good.
Ah, okay. Yeah. So, may I ask you if you would like to make another comment? Anyway, it was very interesting in this night to discover.
Because, of course, from my side, I think it would be really nice that maybe every 5 or 10 years, right, like Marius can make this project again. So, because it's also interesting to compare, right? So, how this city changes, and I can imagine that probably also different. And I believe that such a music also increasing the people have the connection with these three cities, right? So.
Yeah, I would like to ask Andrea if do you, Andrea?
Yes.
What do you think about? Because you presented us this incredible, I mean, almost impossibility to to find the little box for the ideal box. So what do you think? I'm very curious about your reaction, because in fact we have to do in the case of this music. I mean, this incredible composition, universal composition. What do you think about? I'm curious as as a researcher.
Oh yeah, I guess the human reaction was that we think we're doing something incredibly complex, but then we see. I guess if I'm probably taking your question a little bit astray. So what is something that kind of struck me deeply Marius's presentation was, and I guess I apologize because I'm sort of taking your question for a ride, but the sort of solitary, lonely aspect of the kind of research that gets into, sitting at this intersection. It's somehow the walls of interdisciplinarity is that you have to speak two languages, and there are maybe two big communities, and you have to sit at the intersection of them, and that probably doesn't leave you a lot of company. That's sort of kind of day-to-day experience for the kind of research collaborations I'm involved with, and I've seen the masses that were taking part of in the events that Marius is creating, and the sort of human dimension and management, for lack of a better word, of this many people. It kind of made you realize, that there could be other things that are sort of difficult that I am spared in my day-to-day job. I guess there's something that is sort of extreme in the typical setup that you can't see my background. It's kind of blurred, but you can probably see there's a blackboard there, and the creation of advances in quantum geometry largely consists of long afternoons staring at that blackboard in a solitary effort, and it was sort of extreme, and by contrast to see just the sheer number of the enormous the sheer size of the human element that enters these compositions. It was absolutely striking somehow. So I'm sorry if I'm highlighting what for me was an incredibly stark difference from a human perspective in the creation of research and knowledge, and the act of artistic creation in Marius's case compared to what other people do. It's a big spectrum, let me say, even from a human perspective.
Thank you so much. I see that Françoise, would you like to tell us something? Thank you very much.
Yes. First of all, thank you so much for these two very much interesting topics. I have a question for Dr. Marius, Joannou Elia. I wondered, for those different projects and those different totally cultural cities, if he had difficulties in his freedom of artistic freedom to approach some items, or was he totally free to do what he wanted? Sometimes in these contexts of the world economy and aspects of the world, I just wondered if he had the totally freedom, or was he obliged to implement certain topics, or could you just choose what you wanted to do in your project? That's my thoughts of my. I just wonder if there's some answers to this. Thank you so much.
Thank you, Marius. Please unmute yourself.
Seems some spies are inside the system here. So, Francis, thank you very much for your question. I think it's legitimate. I must admit there have been no artistic limitations concerning the context or the intentions that I had to. But I had other complications because I wanted things that they are not, or they didn't sound very easygoing or logical to the ones that were, let's say, there and responsible for their realization. I can say, for example, a recent experience, I wanted to place a performance on the rooftop. And this is in the center of Shanghai, in the Bund, for you who might know, and on the 31st of December. And at the beginning, I got a license because the complications are about licenses. And the moment you are getting outside the common and used or outside the box, so to say, then it's where complications and limitations starts. And the limitations are more of practical concerns than of let's say musical ones. So there we had to go to the police, we had to engage the municipality. By the way, in all these three projects, there are very strong partners that enable us accesses. For example, the municipalities were part of the projects, and some, I would call them institutions, that it's easier to go somewhere other than just going as an artist from the outer environment and wanting to do something. So although it was not possible, with insisting, most of the things happens, but many things also didn't happen. For example, in Kyoto, I was aiming for a session in the Golden Pavilion, for all who knows it, and this was impossible. So no matter what all forces we put in play, they said this is cultural heritage, this is just for what it is, and no intervention, at least in our case, we are not able. And the second also very difficult part is weather, because when you want to do things outside, on the one hand, the weather doesn't always agree so that it gives you the right temperatures. And as you know, musicians don't want to perform when there is heat or when there is cold. And I usually choose the periods for these projects so that the environment, the scenery of the city has something aesthetically to offer. That's why Kyoto was produced during autumn. And
I have two questions from Huyu, also for you, Marius.
Yes.
The question from Huyu. First, what are the local government's attitude towards the projects? Any differences between the three cities? And the second one, if there is any reason that the three cities are from the north part of East Asia.
I think I will start with your last question. I think the reason is that because of the first, let's say, part, Vladivostok became quite successful there. So it was heard, I think, in this region. So this made a very good fundament for the continuation in these, let's say, close-up areas. Because as you know, Vladivostok is opposite Japan, and Japan is also not very far from China in a way. And Japan and China, they are not so good friends, as we know. So I don't know if this was, in a way, or in our case, a positive aspect to show that China is also here and we are powerful and maybe we are better, I don't know. So this was actually the consequences from the first presentation. I don't know if there is any other logic. And on the first question, yes, completely different approaches regarding national authorities and governments. For example, in Russia, I was maybe trying for 2 weeks to get contact and access to the Philharmonic, and they didn't answer, no response, not even this Beluga owner tried to contact them, actually no answer. And all of a sudden, they make a call and then they ask for a meeting. We go for the meeting, and next day they offer us the symphony orchestra ready to perform by, sight reading. So this is not possible in Kyoto. In Kyoto is the opposite. I had to send a couple of months before I go there a very specific plan of what I would like to do. If every detail, who has to be involved, they had to check everything in advance. And when I arrived there, they told me, this is possible, this is not possible, not possible, possible, possible. But I was not happy with what was not possible. So there I interfered, and they had complications with the mentality of the Japanese people. When they say no, there is no reason to maybe convince them that it's still possible, and they didn't think of this one approach. No means no, and no discussion. So this was a very complicated in my case,
You have a lot of stories. You may write novels also about.
yes, a lot of stories.
Thank you so much. I must excuse you because I excuse myself because it's so late and I forgot to stop. Anyway, I would like to read one of the reactions in the chat. Fascinating and challenging topics. Congratulations to both speakers. Very happy to read this for you. And we meet again in the last colloquium on this semester in 2 weeks with Michael Zalka and Beipeng. Very happy. And thank you so much again.